Everybody. In this video, I'm going to go through a couple of examples from the Chapter 9 and Chapter 10 homeworks to show you guys how you can use Excel to do the calculations to do hypothesis tests. So just as a quick review, the basic process for doing a hypothesis test is first you formulate the null and alternative hypotheses. So the null hypothesis has to do with something about the population. So remember, we pretty much never know the actual parameter for the population because it's not practical to survey the entire population. So the null hypothesis has to do with the population parameter. And in your textbook, they made the analogy of in a court case where a suspect is considered innocent until proven guilty. That's kind of the idea of the null hypothesis. So you're going to assume that the population parameter is normal, whatever that means in the context. And we'll go through some examples so you see an idea of what that looks like. And then your alternative hypothesis is that the population parameter, whether it's the population mean or the population proportion, is actually significantly different than whatever that null hypothesis was. So that's your first step of the hypothesis test process. And then you draw a sample from the population and measure the sample statistics because it's much more practical to take a small portion of the population and do measurements on that compared to surveying the entire population. And then you look at the likelihood of observing a sample statistic that's at least as extreme as the one you found, under the assumption that the null hypothesis is true. And when you do this, you'll find the probability of getting such a result, and that's called the p-value. And if the p-value is small enough, meaning the probability that you would get a sample that has the results that you found or more extreme, if it's really, really small, then that means that you can reject the null hypothesis and you have evidence to support the alternative hypothesis. So the way that you determine whether or not it's rare enough or if the probability is unlikely enough is based on your significance level. So it's usually a 5% significance level, but it can also be a 1% significance level. So that's the basic idea of the hypothesis test process. Now, notice that you can do this for either a population mean or a population proportion. And in Chapter 10, we'll also be doing it for multiple sets of data. So in Chapter 9, we're just going to be looking at means and proportions of a population. But in Chapter 10, we'll be expanding that a little bit further. So let's do an example from section 9.2. I'm going to do maybe, I didn't pick a question in advance, so let me just find one real quick. Okay, this is perfect. So I'm going to do question 10 on section 9.2. So this says a poll used a sample of 100 randomly selected car owners. And within the sample, the mean time of ownership for a single car was 6.51 years with a standard deviation of 3.71 years. And we want to test the claim by the owner of a large dealership that the mean time of ownership for all cars is less than 7.5 years. So for our sample, the mean was 6.5, which is less than 7.5. But what we want to see is if this is an unlikely result to get. Because it is possible that we just happened to get a sample that was a little bit smaller than the claimed mean of the population. But it could also maybe be significant. So our null hypothesis in this case is that the mean time of ownership for all cars is equal to 7.5 years. because this is what we're testing the claim against. So this is kind of like the innocent until proven guilty idea. So our null hypothesis, which is denoted with H0, um, is that the population mean is equal to 7.5 years. And then since we want to test the claim that the mean time is actually less than this, so this is our alternative hypothesis, we're going to select this one because our alternative hypothesis is that the population mean is actually less than 7.5. So this means that this is going to be a left-tailed test, and I'll explain what that means in a little bit more detail in just a second. But let's go ahead and record this information in Excel. And I'm also going to be using our formula sheet for the chapter 9 and 10 test. So in this case, since I'm dealing with a population mean, this is how I'm going to calculate my z-score. So I'm going to have my population mean, which was that, I think it was 7.5. Yep. And then I'm going to have my sample mean, which was 6.51. And then my sample standard deviation is 3.71. My sample size is 100. So that's all the information that I was given. And if we look at our formula sheet, the way that we calculate the z-score is we take the sample mean and subtract the population mean and divide that by the sample standard deviation divided by the square root of the sample size. So in this case, our z-score is going to be, and remember to put parentheses around each set of calculations you're doing. So I want to do my sample mean minus my population mean. That gives me the top part of my formula. And I'm going to divide this by the sample standard deviation divided by the square root of the sample size. And that gives me a z-score of negative 2.668. Now, remember what the z-score means. Let me just draw a picture of this really quick. So if we have a normal curve, it looks like this. And the population mean is here at 7.5. A z-score of negative 2.66 means that if you go 2 and a little bit over a half of a standard deviation away from the mean, so we're about right here, that's where our sample mean is. So this is where that 6.51 lies on our graph. And what we're looking at is what's the probability that if you really did have a population mean of 7.5, what's the probability that we would get a sample that has a mean of 6.51, or even more extreme than that? And so we're basically looking for the proportion, or sorry, proportion might not be the right word, the probability of this area. And this is where we can use our norm.dist calculation that we used last week. So I'm going to say that this is the area less than the z-score. So to use that formula again, we just type in norm.s.dist, and then we select the z-score and say true. Or you can also put in the number 1. Either way, it will still work. And that basically tells you that this portion of the normal curve is less than 1% of the entire curve. And that's what our p-value is, because that's the probability that our sample mean, assuming the population mean really was 7.5, that we would get a sample mean that is this much smaller than 7.5, or potentially more extreme. And since that probability is really low, specifically lower than our significance level, that means that we can reject the null hypothesis, and we have evidence to support the alternative hypothesis. So to finish out this problem, to show you what the rest of it would look like, here's that z-score we calculated, 2.6684. Whoops. Oh, maybe I rounded it wrong. Yep, that was wrong. 7, there we go. Okay. And then the p-value that we found was 0.0038. And that's what our p-value was. And then since the p-value is really, really small and it's less than our significance level of 5%, that means that there is sufficient evidence, because this is our alternative hypothesis, is that the mean time is less than 7.5. And so that's what our p-value would, or that's the conclusion we would make. We would reject the null hypothesis, and we would have evidence to support the alternative hypothesis. So that's how you would do this problem. Now, notice that this alternative hypothesis was specifically that the mean time of all cars is less than 7.5 years. And so in our picture, we were wanting to find this probability. Now, sometimes you'll be asked to find the probability or to test the claim that the mean time of ownership for all cars is different than 7.5 years. And what that means is not only are you looking at, is it possible for it to be less than, or what's the likelihood that it's less than, you're also looking at what's the probability that it could be significantly more than. And so if you ever have one of those, you would still use this norm.dis to find the area that's less than the z-score, but then you would double it. So say area less than and greater than the corresponding z-score. So this z-score wouldn't be a negative 2.66. It would be a positive 2.66 because it'd be a little bit more than 2.5 standard deviations above the mean. So if you had that, you would basically just take this number and multiply by 2. So this is what we call a two-tailed test, because you're looking at the likelihood that it could be either less than or more than. And usually the wording for that will say that it's different than the mean of 7.5. The one that we did for this problem was called a left-tailed test. And sometimes you might also get one that's called a right-tailed test, where instead of saying the mean time of ownership for all cars is less than a certain number, it might say that it's more than. So let's say that our sample mean wasn't a number that was smaller than the population mean, but let's say it was maybe like, I don't know, let's say 9 was the mean time of ownership in our sample. You can see here that the z-score is now a positive number, which on our picture would be like some number way up here because it's 4 standard deviations above. And the area or the result that we get when you use norm.s.dist is like 99%, which makes sense because remember, norm.dist gives you the percentage underneath that value. And if we were doing a right-tailed test where we were trying to see if this result of getting a sample mean of 9 years means that like our alternative hypothesis would be that the mean time of ownership for all cars is more than 9 or more than 7.5 years. What we'd be looking for would be the area under this part of the curve. So if you're looking for a right-tailed test, the area that's more than whatever z-score you find is going to be 100% of the curve minus the percentage underneath that z-score. Because norm.s.dis will always give you the percentage that's less than the z-score. And so if you want to know the area that's more than it, you would just do 100% minus it. And let me actually change this to maybe be like 8, so you can actually see the decimal values because those decimals were really small. So like on this one, if your z-score is just 1 or a little bit more than 1 standard deviation above, the area less than is going to be 91%, but that means the area that's more than it is going to be 8%. And in that case, you would also need to change this formula because you wouldn't want to double the 99%. You would want to double the tail, which in this case would be the more than amount. So that's how you would do a problem like that one. So let's look at an example from section 9.3 to explore this idea of left and right tail or two-tailed tests a little bit further. Because the only difference between section 9.2 and 9.3 is that the way you calculate the z-scores is different because in 9.2, you're working with population means, and in 9.3, you're working with population proportions. So the way you calculate the z-score is slightly different, but the basic idea of how you find the p-scores or the probability is very similar. So I'm going to do question 6 from 9.3. So on this one, it says, according to a study in a previous year, 58% of households nationwide used natural gas for heating during a year. Recently, a survey of 2,200 randomly selected households showed that 59% used natural gas. So notice that this new survey is giving a proportion that's slightly higher than the previous proportion. And we want to use a 0.05 significance level to test the claim that the 58% national rate has changed. So I'm going to make a new sheet here. So first of all, let's go ahead and identify our null and alternative hypotheses. So the null hypothesis is that the population proportion is still just the same. So we're going to have that the proportion equals 0.58. And then the thing that we're testing is to see if it has changed. So that means that our alternative hypothesis is that the population proportion is not equal to 0.58. It could mean that it's either increased, which kind of seems like it based on our sample, or it could also mean that it's less than. So this would be an example of a two-tailed test because we're looking to see if it's changed, not specifically if it's less than or more than. So that's the null and alternative hypotheses. And then we need to find the z-score. So I'm going to type in the information that I was given into Excel. So the population proportion is this 0.58. The sample proportion, which in the formulas is denoted with the p hat symbol, this is going to be 0.59. Our sample size, sample size is going to be 2,200. And now I'm going to calculate my z-score, using the formula on my formula sheet. So I don't know why it's not letting me move it. There we go. Okay, so my z-score in this case is going to be equal to p hat. I'm going to put this in parentheses because I want to do each part of my calculation in the right order. So I'm going to take my sample proportion, subtract my population proportion, and divide that result by the square root of, in parentheses, the population proportion times 1 minus the population proportion divided by, oops, and I should say that I want to multiply these together. Let me just make sure I've got my parentheses right. Okay, so I've got all of that. I want to divide that by the sample size and then close my parentheses for the square root. And that gives me a z-score of 0.95. And it says round to 2 decimal places. So I'll go ahead and do that. 0.95. And remember, what that is telling me is on my normal curve, if I have my sample proportion in the center, if I go 1 standard deviation away, it's actually slightly less than 1 because it's 0.95, that's where this new proportion is. So it's slightly above the proportion that I originally had, the 58%, but it's not like super far above it because it's less than 1 standard deviation. And what we want to find is we want to find the p-value for this test statistic. So because this is a two-tailed test, I'm looking at how likely is it that I get this changed proportion of 59% or something more extreme, and specifically it's more extreme in either direction because I'm testing the claim to see if the proportion has changed, not necessarily just that it's greater than. So I'm looking for this portion of the normal curve as well as this portion. And the combination of both of those is what my p-value will be. So to calculate this in Excel, I'm going to use the norm.s.dist function of my z-score, and I'm going to say true. And this percentage, remember, is describing this part of the graph because norm.dist or norm.s.dist will always give you the percentage that's less than whatever z-score you give it. So we'll say this is less than the z-score. Now, that blue part of the graph isn't what I want. I want the 2 green parts. So I'm going to figure out what one of the green parts is by figuring out the percentage that's more than the z-score. So this is going to be 100% minus that blue part. And that tells me that this one tail of green is 17%. And since I'm looking for both of the tails of green and it's a symmetrical graph, that means my two-tailed p-value is going to be this one green tail times 2. And so that tells me that it's 34% likely that I could get a sample that gives me this different value or something that's more extreme. And since 34% is not super rare compared to the 5% significance level, that means that I cannot reject the null hypothesis. So I'll type in my p-value as 0.3419. And then I do not reject the null hypothesis, which means there's insufficient evidence to support the claim that the percentage of households using natural gas has changed. And that's how I would do this one. Now, if that problem, if I'd gone through that whole process and this two-tailed value had been like 0.001 or 0.002 or something like that, basically any number that's less than your significance level, then you would reject the null hypothesis and you would say that there is sufficient evidence to support your alternative hypothesis. And that's how you would do that problem from 9.3. Okay, now let's go through an example from chapter 10. So this is from chapter 10.2, which is about two-way tables. and doing hypothesis testing with those two-way tables. So one thing that's important to note is that the two-way tables doesn't mean that you just have two options. It means that you have two categories or two sets of categories that you're grouping your data by. So for example, on this one, we have homicide, robbery, and assault. I think these are uh, just crimes that were committed. And then you have whether the criminal was a stranger or if it was an acquaintance or a relative. So even though there's three options here, it's still a two-way table because you have two categories. You have the type of crime, which has three options. And then the second category is the relationship that the criminal had to the victim. So I'm just going to go ahead and download this really quick so that we have that. Okay. So, oh, there we go. Okay, so the basic idea of a two-way table hypothesis test is you're going to test whether or not the two variables are related to each other. So in this case, we're looking at whether or not the type of crime is related to the relationship between the criminal and the victim. And the way that we do this is similar to the process we use in Chapter 9, except that our null and alternative hypotheses will look slightly different, and the calculations that we make to find the p-value are also slightly different. Or I shouldn't say p-value, the critical value that we find will be slightly different. So first of all, whenever you're doing a two-way table hypothesis, the null or hypothesis test, the null hypothesis will always be that the two variables are independent of each other. And then the alternative hypothesis is that the two variables are related. So the correct option on this one would be that the null hypothesis is that the type of crime is independent, whether the criminal is a stranger or not. And then the alternative hypothesis is that the type of crime is somehow related to whether the criminal is a stranger or not. So the null hypothesis will always be that the two variables are independent. Alternative will be that they're related in some way. And then the way that I would figure out whether or not I can accept or reject the null hypothesis or not is based on the expected value and the chi-squared value. So the way that you find the expected value is you take the row total multiplied by the column total and divide that by the grand total. So if we look at this data here, we just have the individual measurements. So like this tells us that 14 of the crimes were homicides where the criminal was a stranger to the victim. 382 robberies were where the criminal was a stranger, and so on. So in order to have the row and column totals, we need to actually calculate those out. So the way that you do that is with the sum command. So I'm going to hit the equal sign and then type in sum. And I want to select all of the stuff I want to add up. So since I'm finding my row total, I would sum up those three cells. And you can type that in for each one. But Excel is also really nice because if you copy and paste a formula, like this one is summing up B2 to D2. If you copy and paste it, Excel will automatically adjust it for the for the row. And that's also true if you do a column total. So if I do sum of these two, that will give me that total. And if I copy and paste that, you can see that it automatically adjusted it for column C and column D. And then to find the grand total, you can either add up the columns or the rows. It will give you the same thing either way. But I'm going to add up that. Or I guess another way you could also do it is just add up all of these, regardless of whether you add these two together or these three together or the total of the 6 we were originally given, all of them will give you this same result here. So that's how we get these individual calculations of the row total, column total, and the grand total. And now we want to find the expected frequency of each cell. So I'm going to copy and paste this down here. And I'm going to delete these values because I'm going to now find the expected ones. So for the homicide one, I'm going to take the row total, multiply by the column total, and then divide this by the grand total. And what this is telling me is that if these two variables were independent, I would expect that I would have about 31 homicides where the criminal was a stranger. And that's actually pretty significantly different than the number that I have here, which is 14. And then I'm going to continue doing this. So for a homicide where the criminal is an acquaintance or a relative, I'll do that row total times my column total divided by the grand total. And then for the robbery, do the same thing. Row total times column total divided by grand total, and row total times column total divided by grand total. And you can see that these numbers are pretty significantly different than what we've got so far. So it's likely that we're going to reject our null hypothesis and say that there is a relationship between whether a criminal was a stranger or acquaintance and the type of crime that was committed, just based on looking at these numbers and the fact that these are pretty different. Because these expected calculations that we're looking at is what you would have if the crimes really were independent of each other. If the two variables were independent of each other. So I'm just going to go ahead and finish doing this calculation. Okay, awesome. So we've got all of those numbers here. And now we want to calculate the chi-squared value. So chi-squared is the sum of this calculation for all of the cells. So I'm going to calculate this again, and maybe it'd be good to label these so that we know what we're doing here. Just delete those. Okay. So this table here was observed frequencies. This one here is the expected frequencies. And then this is the chi-squared calculations. Okay, so the way that you find the chi-squared thing is we need to find this calculation for each individual cell. So for this cell, I'm going to do the observed frequency. I need to put this in parentheses. So in parentheses, the observed one minus the expected one, and I'm going to square that by raising it to an exponent, and then divide by the expected frequency. And that gives me this value for just this cell. And then I need to do that for all of the other cells. And this is where Excel's structure comes in nicely, because if I copy and paste this to all of these other cells, you can see that it automatically adjusted it for the placement of each cell. Oops, don't want to change that formula though. So these are all of the individual calculations of the observed frequency minus the expected one squared, and then divided by the expected. And our chi-squared value is the total of all of these. So this X looking symbol, that's the letter chi in the Greek alphabet. So the chi-squared is going to be the sum of all of these. So I'm going to type in equals sum of all of these values. And that gives me a chi-squared value of 118.4. Now, whether or not this is a significant difference is based on this table here. And the table is based on the size of the original data set that you were given. So in this case, we're dealing with a 2x3 original data set. And so if we're looking at a significance level of 0.05, our chi-squared value would be 5.91 as our critical value. So since our value is much bigger than that, that means that we can reject our null hypothesis. But if this number had added up to like 4.5 or something that was less than 5.99, then we would not be able to reject our null hypothesis. And similarly, if you have another significance level, like a 1% significance level, you would have a slightly different critical value. But in this case, I haven't filled out all my stuff yet, so let me do that really quick. Okay, so the expected frequency was 31.2. For the robbery, it was 286.7. For assault, it was 806.1 and 21.9 or 8, yes. And 200.3 and 562.9. So that's basically filling that part out. And then the chi-squared value was 118, and they want me to round to the nearest thousandth, which is the third decimal place. So I'll round it to that. And then since our chi-squared value was so much bigger than the significance level at, we were actually going at 0.01, so we'd actually compare it to this one. But our chi-squared value is still much bigger than that. And our critical value for this would be this 9.210 that was given. And since our chi-squared was bigger than that, we would reject our null hypothesis, which is that the relationship of the criminal is independent or doesn't relate to the type of crime. And we would say that there is evidence to support the claim that the type of crime appears to be somehow related to whether the criminal is a stranger or not. And that's how you would do a two-way table hypothesis test. And then the last example I'm going to go over comes from section 10.3. So this is where you do ANOVA testing. And in 10.2, we looked at when you have two variables in a two-way frequency table, you look at whether or not those two variables are related or independent from each other. And with ANOVA testing, you'll have multiple different categories, and then you're looking to see if the means of each of those categories are about the same, or if there's any one or maybe more of them that are significantly different from each other. So when you do ANOVA testing, the null hypothesis will always be that the means are equal to each other. So in this problem, it says in a car crash experiment, cars are classified into one of four groups, either subcompact, compact, midsize, or full size. And there's 5 different cars in each group. So in this survey that they did, or this study, there's 5 different cars in each category. And we're looking at head injury data where the dummies in the driver's seat are listed in the table. So these numbers represent the severity of the dummy headed injuries. And we want to use a 0.5 significance level, and we want to test the null hypothesis that the different weight categories of cars have the same mean in terms of head damage or head injuries. So the null hypothesis is going to be that regardless of what size of car you have, the head injury severity is about the same. So I've already answered that question here, but that's what our null hypothesis is. And then the alternative hypothesis is that at least one of these means is significantly different from the others. So to calculate this, I'm going to download this in Excel. And you could technically do the ANOVA calculation by hand, but it's like super, super hard. So you pretty much always want to make sure you're using Excel to do this type of calculation. And to do this calculation, you're going to need an add-in, and it's the XL, let's see what the actual name is, XL Minor Analysis Tool Pack. So this used to be called data analysis. And that's what your textbook calls it, but excuse me, Excel changed the name of it. So it's called XL Minor Analysis Tool Pack. And the way that you add it is you just click this add-in button on the home tab, and then you search the add-ins for XL Minor Analysis Tool Pack. And then to do an ANOVA test, you're going to do ANOVA single factor. And then for your input range, you're going to select the whole set of data that you were given. And some data sets will be given to you in columns, like this Excel spreadsheet. So you would select columns. Other data sets might look more like this, where it's given to you in rows. So you just select whichever one applies. In this case, it's columns because that's the way our Excel spreadsheet is structured. And then the significance level is the alpha value. So it automatically set as a default of 0.05. But if the problem had told us to use a 0.01 significance level, you would change that. And then the last thing you need to do is just select where you want the data to be calculated. So you can just select any random cell as long as it won't run into your data. And then when you click OK, you're going to get a whole bunch of data here. So it gives you this summary, it gives you all of this stuff. But the two important things we're going to look at are the F test statistic, which is this number here, and then the p-value here. So our F statistic in this case is 0.925. So since it's a 5, that will round up to 3. And this is kind of, this is like a test statistic that's specific to the ANOVA test, just like the chi-squared test statistic was specific to the two-way tables. So you don't have to know exactly where this comes from because Excel will do all the calculating for you because the calculation is actually pretty complicated. And then the p-value is going to be 0.166. So about 16%. And since our significance level for our p-value is 0.05 and our p-value was 0.16, that means that we can't reject the null hypothesis because the differences between the means in this data set are not significant enough to say that it's not just due to chance. So we will not reject the null hypothesis, which means that there's not sufficient evidence to conclude that larger cars are safer based on this data that we were given. So that's how you do an ANOVA test. If you have any questions, please let me know, but I hope that this was helpful for you.